op amp with T or pi network in the feedback path. Look at this circuit. See, in the feedback path so far what we observed is a resistor. Now instead of a single resistor, I am taking one pi network first. Okay, just for time being, I'm taking all equal resistors. It's just to save the time and make the analysis simple. Nothing else. Okay, you can have any resistor of your choice. Doesn't matter. Or let me take this one R1, R2, R3 and R4. No issues. Okay, then the same circuit, if you observe, so due to virtual short, here the voltage will be 0. And this is output. Okay, we are well aware of this point. Here what I am doing is just look at this resistor R3. This point and this point are one and the same. I can show R3 from, instead of showing R3 from here to ground, I can show R3 from here to ground. Possible. And look at R4. R4 is from here to ground or from here. This point and this point are one and the same. So here to ground only. Okay, R3 and R4 positions I can change. So I'm redrawing the circuit this way. R3, R2, VI. Anyway, R1 is between inverting input terminal and output. R1 and R4 is from output to ground. See this. Okay. So now due to virtual short it is 0. R3 can be eliminated. No current is possible through this. We can eliminate R3 and R4 is nothing but the load resistor. Acts like load. So is it necessary to worry about this R3 and R4? Nothing to worry about them. We can just discard them. Finally, what is the output? V output is equal to, this is same as that of our basic circuit only. This is what I told you in the previous lecture. So it is minus R1 by R2 times VI. That's it. A very, very simple one. If you have some pi network in the feedback part. Whereas if you have the T network, directly I took the question like this. Equal resistors. Equal or unequal, the procedure remains the same. So the most common thing is, okay, you can convert this T into, right, pi network, and we can write it. That is one way of writing it. Okay, let me do that way, or there is another way of doing it so also. So here I can write one resistor. What will be this resistor, friends? It is 3R. Again here one more resistor whose value is 3R, and one more resistor whose value is 3R. We know that. Star delta conversion. Okay, outside resistors values will be more. And further, this is similar to the previous case. So this 3R, I need not worry about this 3R and this 3R. Is it not so? Once it is converted into a pi network. So finally what I can write here, 3R R VI, and finally it is minus 3R by R into VI minus 3 into VI, or the gain is equal to minus 3. So option C is correct. So we can write this way. or alternatively there is another way of writing it, the most common way, instead of converting that star into delta etc. Okay, if you want you can do it, but the much better way of doing is, I want to generalize it, right? However the op-amp circuit appears, what we are doing, we are applying virtual short, next we are taking the nodal analysis, right? Most of the op-amps problems can be done with the help of nodal analysis. So let us have a look at that approach. Minus plus, we output R, VI, R and R. Okay, due to virtual short, it is 0 minus. So V plus is equal to 0 and V minus is equal to V plus is equal to 0 due to virtual short. We know. Let me take this voltage as Vx. Anything we can write it, or Va. Okay, then apply. Let me write it as Vb otherwise. Okay, and this is node A and it is node B. Apply KCL at node A. What we can write, 0 minus Vi by R plus 0 minus Vb by R is equal to 0. So what is Vb here? It is minus Vi. Anyway, in case of the basic inverting amplifier, we are well aware, right? Minus plus. Suppose I have a circuit like this, RRVI, and due to virtual short, it is 0 volts. And if I take this as node A, what is the voltage at this point? We are writing, right? This Vb is similar to the output here. Is it not so? Just by taking node equation here, 0 minus Vi by R plus 0 minus V output by R, or V output is equal to minus Vi. Is it not so? The same way, Vi means minus R by R into Vi, blindly I can write it. Just what is the result of this node equation? By taking a node equation here, we are getting the voltage at the next point, which can be even written directly as minus R by R into Vi. Just like that you can write it. Keep this point in mind. Or you can take the nodal analysis, nothing to worry. Okay. Next, KCL at node B. So Vb minus 0 by R plus again Vb minus 0 by R plus Vb minus V output by R is equal to 0. So what is V output? I can cancel this R. V output is equal to 3 times Vb. So what is Vb here? Minus Vi. So minus 3 into Vi. Our gain AV or ACL is V output by Vi is equal to minus 3. Okay, simple two node equations, nothing else. Instead of using star delta conversion, we can write this. Why I am telling so means, is there any guarantee that the resistors are always equal? No. It may be some 2K, 5K, 7K like that. Then star delta conversion will kill the time there. Of course, there, if you understand the actual concept, you need to find this particular resistor by discarding the remaining two. Once you find this resistor, then this resistor by this resistor gives us the gain, with, of course, with negative sign. That's what you can do. Okay, so that is another way of understanding this. But most common thing, instead of going with n number of methods approaches, let us take a procedure which can be applicable to any problem. Right? That's what my concern. That's why I'm saying so. Better go with nodal analysis. Star delta is also fine. You can just find this particular resistor. Sorry. And we need not worry about these two resistors because we have seen earlier star delta conversion, right? Those two do not play any role. Okay. Next, I'm extending it. Okay. Again, you can convert it into that star delta conversion and write it, or the basic nodal analysis. So here I'm taking here due to virtual short, it is 0 volts. Let me take it as node A, and this as node B. This voltage is VB, and this is node C, and the corresponding voltage VC. Right, and first node A, by applying KCL at node A directly, we can find the voltage at the next node. What is VB? Minus R by R into Vi. I told you. So just for our understanding purpose, I am writing KCL at node A. What you can write by taking this node equation, you can see the voltage at the next point. VB is equal to minus R by R into Vi minus Vi, which we observed in the previous problem also. Next, by taking this node equation, we can find the voltage at this point. This VC is the same as that of V output of the previous case. Is it not so? Okay, or VC is equal to 3 times VB. Blindly I can write it, where VB is equal to minus Vi. So VC will be equal to minus 3 times Vi. Okay, we can write it anyway. Just I'm writing KCL at node B. What it gives us, by taking this node equation, we can get the voltage at the next node. See, I know this voltage and this voltage. What is unknown? This voltage. So by taking this node equation, we can find the unknown node voltage VC. Anyway, it is VB minus 0 by R plus VB minus 0 by R plus VB minus VC by R is equal to 0. R cancel. VC is equal to 3 VB, which is equal to minus 3 into VI. Absolutely. Okay, so previous case output, right? VC is just nothing but the output of the previous case. Okay, next I'm taking this node equation. So here VB is equal to minus VI, we are well aware, and VC is equal to minus 3 VI. Done. So by taking this node, these two voltages, we can find the voltage at this point. So let me apply KCL at node C. Two voltages are known and third node voltage can be easily found. So KCL at node C, that is VC minus VB by R plus VC by R plus VC minus V output by R is equal to 0. So V output is equal to 3 VC minus VB. It is VC is equal to minus 3 into VI, and minus VB is equal to plus VI. So it is minus 8 VI. That's it. Anyway, it is an inverting amplifier. Okay, like this you can proceed. That's why I told blindly we can go with nodal analysis. Here for my convenience sake, I took all equal resistors. The resistors need not be equal. Then also you can blindly follow with this processor instead of using star delta conversion, etc., etc. This nodal analysis is much simpler. Next, say this question. In the circuit shown, assume that the op-amp is ideal if the gain V output by V input is minus 12. The value of R in kilo ohms is. What is the value of this resistor they are asking? Gain is given. The procedure remains the same. Due to virtual short, it is 0 volts. Let me take it as node A and it is node B. This voltage is VB. We know what is VB. VB is equal to minus 10K by 10K into VI. So anyway equal, so I can write it directly minus V input. If this is also 10K, then output is V output by V output might be minus 3, but this is other than 10K, that's why you are getting 12. Okay, let it be. So let us find, anyway all are in kilo ohms. Let me take this is also kilo ohms. I'm just writing R kilo ohms. Then let me apply KCL at node B. What we can write? It is VB minus 0 by 10K plus VB minus 0 by R kilo ohms plus VB minus V output by 10 kilo ohm is equal to 0. I am writing R kilo ohms, I am assuming, so that I can comfortably cancel K. Okay. Next, V output is equal to, or VB by 10 plus VB by 10, it is VB by 5. VB by 5 plus VB by R is equal to V output by 10. So, we can break. So, VB into R plus 5 by 5R is equal to V output by 10. Anyway, 5 twos we can write. Okay, but what is VB? VB is equal to minus V in. So, minus V in into R plus 5 by R is equal to V output by 2. Implies what is gain? V output by V input is equal to, okay, 2 into R plus 5 by R with negative sign, whose value is equal to minus 2. Okay, so 2R plus 10 is equal to, implies 12. So what is R then? R is equal to 1 kilo ohm. I mentioned R in kilo ohms. So R is equal to 1 means it is 1 kilo ohm. R kilo ohms means R is equal to 1. Okay, R in kilo ohms means answer is 1. Okay, that's it. This is how we can solve this problem. The regular method. Assume that the operational amplifier to be ideal. The gain of the circuit shown in figure is. You see, it is just something similar to the previous one only. Here 10K, 10K, and it is 1 kilo ohm. So same T network, here instead of 10K, what we have here? 1 kilo ohm. Okay. So definitely the gain is minus 120. You can check that. Anyway, directly, as it is an extension to the, right, similar to the previous problem, I wrote the answer directly. We can just check it. What is the gain of this circuit? Anyway, due to virtual short, it is 0 volts and it is node A and it is node B. Okay, it is VB. What is VB? By taking this node equation, we can find the voltage at this point. So, KCL at node A, VB is equal to minus 10K by 1K into VI, that is minus 10 into. Okay. Then next KCL at node B. VB minus 0 by 10K plus VB minus 0 by 1K plus VB minus V output by 10K is equal to 0. V output is equal to, right, anyway kilo cancel, VB plus VB by 10 plus VB by 10, that is VB by 5, VB by 5 plus VB, it is 6 VB by 5, V output by 10 is equal to, okay, so 5 2's. So implies what I can write, V output is equal to 12 times VB, but VB is equal to minus 10 into VI. So what is the gain here? V output by VI, V input, it is equal to minus 120. It's a very, very simple question. Okay, right. Earlier VB is equal to minus VI. Now it is 10 times. Okay, that's why here the multiplication factors, gain factors change. Anyway, now instead of giving input to the inverting terminal, we are giving input to non-inverting terminal. The procedure remains the same. If you want, you can use star delta conversion and do it. I have no objection at all. But I just go with a general procedure, universal procedure I want to use. So virtual short, it's not 0, it is V input. And let me take it as node A, and this voltage as VB and node B, and finally. So here this voltage is 0, and this voltage is V input. By taking this node equation, the unknown voltage VB can be found. Once you get VB, then we know this voltage and this voltage. So we take the node equation here so that we can get the voltage at this particular point. A very simple approach. So again, what is VB? We can write it is like a non-inverting amplifier output. VB is equal to 1 plus R by R into VI. Blindly we can 2 times VI in this example. Okay. So KCL at node A, then it is V in minus 0 by R plus V in minus VB by R is equal to 0. So VB is equal to 2 into V input VR value. Okay. We can take so. Right. A non-inverting amplifier output. What is the result of the node equation here? We know here the voltage here is 1 plus R1 by R2 into voltage at the inverting terminal. That's what we have taken. Okay. Next, KCL at node B. VB minus VI by R plus VB minus 0 by R plus VB minus V output by R. So what is output then? It is 3VB minus VI. I can take so. What is VB? It is 2 input, 2 times input. So it is 5 into VI. What is the gain of this circuit? It is 5. Option A is correct. Okay. Earlier, star delta might be right looking like a bit easier because we are removing 2 resistors as the non-inverting terminal was at ground potential. But here it is not so. So that right the analysis becomes a bit lengthy. That star delta conversion. Next, look at this question. For the circuit shown below, assume that the op amp is ideal. Which one of the following is true? Okay, what is the output? It is just the previous circuit only. They are similar to the previous one. They are just showing it so. Okay, see this. What I can do is instead of show this first. Okay, this 2R I am writing from non-inverting terminal to ground. 2R, and from input to non-inverting terminal another 2R is going. Next, from inverting terminal to ground 1R. Next, from inverting terminal to output 2 resistors R and R. And between these two R's we have one more R which is going to ground. So it is the same circuit what we studied. Just to confuse us, they gave like this. Okay. Then how fast you understand the circuit, that matters. That much you can save the time. It all comes with practice. Practicing a number of problems. Okay. So anyway, once I know the voltage at the inverting non-inverting terminal, output is equal to, if I say this voltage is V plus due to virtual short, this is also V plus. V minus is equal to V plus. So what is output? 5 times V plus. But what is V plus? It is Vi by 2. Is it not so? So voltage at the non-inverting terminal is Vi by 2R plus 2R multiplied with 2R. So it is V input by 2. So implies, anyway, V output is 5 times voltage at the non-inverting terminal due to virtual short. It is 5 by 2 into Vi. That is 2.5 times Vs. Vi. Okay, there is a printing mistake. I should write here Vs. Okay, and here also it is Vs. 2.5 Vs. See how simple questions they are asking. Next. Okay, non-inverting terminal, right? Also input is given to non-inverting terminal and multiple T networks, and the procedure remains the same. Right? Let me take due to virtual short. It is Vi node A, Vb node B, Vc and node C. So Vb is equal to 2 times Vi. Directly I am writing. And next, by taking this node equation, we will get the voltage at this point. How much it is? 5 times Vi. I am directly writing just from the previous knowledge. Knowledge we acquired from the previous problem. Okay. Next, if I take this node equation, then automate this voltage is known, this is known. If I take this node equation, I can find this unknown voltage. That's it. So KCL at node C. Vc minus Vb by R plus Vc minus 0 by R plus Vc minus V output by R is equal to 0. So what is V output? 3 Vc minus Vb. It is 3 into Vc is 5 into Vi minus Vb is 2 into Vi. It is a 13 into Vi. Okay. V output is equal to 13 into Vi. Very simple. Okay. Determine the output voltage V0 of the circuit shown below. How do we find the output here? Right. So here I can see one node, and due to virtual short it is 0 volts. Let me take this as node A and this as node B. Here this is V output, means this is also V output. Okay. Then let us take node A, KCL at node A. 2 milliamperes is entering, 2 into 10 power minus 3 is equal to, leaving currents I am writing, it is, let me take this voltage as VA. Okay, VA minus 0 by 5K plus VA minus V output by 10K. Okay. So these are the two leaving currents. This is one current leaving current, and another leaving current. Right. Then it is entering current is 2 milliamperes. Okay. Then here what we can write further. Anyway, 2 milli, right, and 5 kilo ohm means I can cancel this milli kilo in the denominator. Then VA by 10 plus VA by 5 plus VA by 10, how much do we get? 3 VA by 10. Okay, so V output is equal to 3 VA by 10 minus 2. Okay, Oh, three currents, no? One is entering current, one leaving current, and this one I wrote and this one I forgot, sorry, plus VA minus 0 by 20k. So this is also cancelled. Sorry. So VA by 5 plus VA by 10 plus VA by 20. So what is their LCM? 20, no? 5, 10, 20. So 20 is their LCM. So VA into here, what do you get? 4 plus 2 plus 1 by 20 minus V output is equal to 2. V output by 10. Sorry. So what is V output? V output is equal to 7 VA by 2 minus 2. Okay, keep it aside. This is one relation between V output and V input. Sorry, V output and VA. Okay. Keep it aside. Next, let me take this node equation. Don't take any node equation at the output because, okay, here no issues. But the thing is, we do not know this current. This current is not known to us. Some current is going into the output terminal of op amp now. So don't do any experiment. Don't take any node equation at the output. Okay, not at all advisable. Just node B. Let us take node B. KCL at node B. That is 0 minus VA by 20k plus, okay, 0 minus V output by 10k. So as far as this node is concerned, only two currents. So it's like a simple inverting amplifier configuration you can see. Anyway, it is 0 minus V output by 10k is equal to 0. So it is 2. V output is equal to minus VA by 2, or VA is equal to minus 2 V output. Now let us take this equation. Let me take it as equation 1 and equation 2. From 1 and 2, V output is equal to 7 by 2 into VA is minus 2 V naught minus 20. So 2 and 2 cancel. It is minus 7 V naught is equal to, okay, minus 7 V naught minus 20. So 8 V naught is equal to minus 20. V output is equal to, how much do you get? Minus 2.5 volts. Okay, that's it. This is how we can find this. See, there is nothing else, simple nodal analysis only. Okay. we keep on taking this nodal analysis, nothing else. Okay, see this question. Consider the linear circuit and with an ideal op amp, not D, with an ideal op amp shown in the figure below. The Z parameters of the two-port network or two-port feedback network are Z11 is equal to Z22 is equal to 11 kilo ohms and Z12 is equal to Z21 is equal to 1 kilo ohm. Okay. The gain of the amplifier means what is V output by VI, they are asking. Okay, let it be. So we know the two-port network equations. Like what are the two-port network equations? V1 is equal to Z11 into I1 plus Z12 into I2 and V2 is equal to Z21 into I1 plus Z22 into I2. We are well aware. So what might be V1? V1 means the voltage between these two terminals. So due to virtual short, it is 0. So what will be V1 then? It is ground and here also it is 0. So definitely V1 is equal to 0. Okay, or I am writing here V1 is equal to 0. Okay. And what about V2? V2 means this point and V output are one and the same. So V2 is equal to V output. Okay. And what about I1 and I2? I1 means this current is I1 and this current is I2. So from where this current is possible? See, whatever the current that comes here, entire current has to go like this only. So what is I1 then? VI, right? The gain of the amplifier. I means let me take it is VI and V output. VI, I1 is equal to VI minus 0 by 1K. So few things we understand from that, from the circuit is V1 is 0 and V2 is nothing but our output and I1 is equal to VI minus 0 by 1K, that is VI by 1 kilo ohm. Okay, so this is what we can take. So what we need to find? V output by VI from this. Okay, let us take this equation 1. Equation 1 implies V1 is 0, Z11 it is 11 kilo ohm into I1. What is I1 here? It is VI by 1 kilo ohm plus Z12 it is 1 kilo ohm into I2. So kilo and kilo cancel. Okay. So I1 is equal to, from this I can write I2 is equal to, okay, minus 11 into VI multiplied with or milliampere. I2 is equal to 11 VI milliamperes. Okay, because here this kilo and kilo get cancelled and I2 is equal to minus 11 VI milli. We can write. Okay, done. Simple networks, I am not doing anything much. Next, let us take the second equation. V2, right? V2 means V output. Equation 2 implies V2 means instead of V2, I can write V output is equal to Z21. It is 1 kilo ohm into I1. What is I1, friends? VI by 1 kilo ohm plus Z22. It is 11K multiplied with I2. What is I2 here? It is minus 11 VI into 10 power minus 3. Okay. Here kilo and kilo cancel and here kilo and milli cancel. So Vi minus 11 Vi, it is equal to minus 120 Vi, we can see. Vi minus 121. So or the gain is equal to V output by Vi, it is minus 120. That's it. Okay, we know the jet parameter equations, and I substituted the values of V1, V2, I1 which are available. From that I found I2 in terms of Vi. Let it be. So these are all just rearrangements only. Next, second equation I took, and after substitutions you can see the gain. Okay, op-amp adder circuits, we will see this in the next section.